Welcome, everyone. Today, we're talking about solar energy. Okay, so we're going to start by talking about the significance of solar energy in our energy systems and the different ways that we harness the solar resource. So remember from the Introduction to Renewable Energy lecture, there are really three main ways that we categorize renewable energy resources. And solar energy is part of the truly renewable energy resources, where use of the resource, the sun, doesn't deplete or impact the sun's ability to shine. So we've got that big fusion reactor in the sky that's providing this resource. So you already know that most of our energy resources track their origins to the sun. And today we're really going to talk about how we harness the heat and light energy from the sun directly to produce energy. And we can use that heat and light in different ways, right? You can install a window to bring in light. You can build thermal mass into your building to capture heat. To use at night to keep your building warm, or you could manufacture a photovoltaic cell, a PV cell, to generate electricity from sunlight. There are really four main methods by which we harness the solar resource. The first is that really simple indirect method. That's everything from using windows for light to leveraging the sun for thermal mass, et cetera, in a building. So, this room obviously is not optimizing usage of the solar resource, right? You don't have any windows, you don't have any way that we're bringing that in. So this indirect method, it's not really measured, but it is the most prominent way that we use the solar resource. And the main way that we can take advantage of it is by smart building design, something that you'll talk about with Joel and with Peter Rumsey later in this class. The second method is the direct use of solar energy to generate thermal heat, which involves using any simple heat trapping mechanism, material to capture heat from the sun and transfer it to various direct end uses, like household water or space heating or swimming pool heating. And then the third method is solar photovoltaics, solar PV, which generates electricity from sunlight by wiring semiconductor materials together that generate a current when they're hit by photons. And then the fourth method is solar thermal electric, which is also known as concentrating solar power, or CSP. And CSP uses mirrors or other types of reflectors to reflect sunlight on a centralized area to generate heat, to heat up water, to generate steam, to turn a steam turbine, and generate electricity. Today, we're really going to focus on solar PV because it's the most prominent way, at least measured way, that we harness the solar resource today. It surpassed solar thermal heat in 2017, and it's experiencing the most growth, not just in the US, but worldwide. And solar PV, it's a very elegant way to generate electricity. There are minimal moving parts. There's no mechanical conversions. There's no thermal conversions. You don't need a lot of water like the traditional thermoelectric power plants do. So it's a really significant change to how we've generated electricity for about a century now. So again, our favorite chart in this class, the unsubsidized levelized cost of energy of different electricity resources. And it shows that at the top, you've got the different solar formulations. And you can see that solar PV makes up some of the most expensive new electricity resources that we can build on the grid today with rooftop solar, to some of the least expensive with utility scale solar PV. And we'll talk a little bit more. CSP isn't on here because we aren't really building a lot of concentrating solar power, at least here in the US. But we'll talk about why we've got this cost differential between utility scale solar PV and rooftop later on in this class. All right, so solar, it's a relatively small portion of our energy mix today. You can see here 2%, 1 to 2% in our energy mix, and then a little bit higher in our electricity mix, 5 to 6%, depending on if you're looking at the US or the world. But it's the fastest growing energy resource, both worldwide, as you can see in the chart on the left, that shows 5-year growth rates of different energy resources, as well as in the US, where you can see that we've gone from pretty much no solar electricity generation about 15 years ago to a significant amount, 5 to 6% today. And most new capacity that we're building today on the grid is solar capacity. This is a zoom in of the capacity chart that you've seen before in this class, and you can see that we're by and large building solar, as well as some wind and natural gas, and increasingly battery energy storage as well. And remembering from the Intro to Renewable Energy class, solar is one of those resources where we've really overshot expectations in terms of growth because of continued innovation in the solar resource and accelerated cost declines. So it's a good reminder that humans have a tendency to underestimate the capacity for change. And the solar resource, it's really large, right? It dwarfs our global energy consumption. And as we talked about in the US context, the solar resource has the technical potential to meet our electricity needs about 75 times over. So we're nowhere near taking full advantage of the solar resource in terms of our overall electricity mix. All right, so let's talk about the solar resource and how we characterize the solar resource. The solar resource, it's pretty much everywhere, right? Everywhere that the sun shines. And there are certain areas like in Australia or particularly Northern Australia or the southwestern US that have more solar resource than others, but generally it's economically viable to develop the solar resource, the solar PV resource, almost everywhere. So a few important terms that help describe the solar resource. The solar resource can be measured in terms of insolation, which is the amount of solar energy that hits a particular surface area over the course of a period of time, like an hour or a day. Or in terms of irradiance, which is the amount of solar resource that hits a particular surface area when the sun's at a 90-degree angle to the Earth. So the left map here shows irradiance, watts per meter squared. The map on the right shows insolation, the kilowatt hours per meter squared per day. Okay, so 2 additional terms that are useful when describing the solar resource. You've got diffuse and direct radiation. Direct radiation describes solar radiation that travels in a straight line from the sun to the Earth without being disrupted by molecules and particles in the atmosphere. But diffuse radiation describes radiation that is disrupted by particles in the atmosphere, things like clouds or air pollution. So in the middle of a clear sunny day, typically the amount of direct radiation that we're getting from the sun is about 85%, and the remainder is diffuse. But if it's a fully cloudy day where you've got 100% cloud cover, you can't see the sun, then that's 100% diffuse radiation. And this is significant in the context of energy because some solar resources, solar technologies can take advantage of both, and some can only take advantage of direct. So solar PV can capture energy from both diffuse and direct radiation, but technologies that use reflectors and mirrors, like concentrating solar power, can only take advantage of direct radiation. And because of that, they have to be, they're typically sited in areas that have very limited cloud cover during the year, in particular desert areas. But as you guys know, concentrating solar power also needs water because it uses the traditional steam cycle to generate electricity, which creates some challenges, right? If you have to site these in the desert, but you don't have access to water, that's a challenge. All right, so let's talk about solar photovoltaics and the technology itself. There are a few different formulations of solar PV. You've got different semiconductor materials, different device types, different structures for supporting the PV panels. And what you choose is likely going to depend on your particular application. So for example, in the early applications of solar PV in the 60s and 70s were really in the space industry for satellites and probes. And the space industry was optimizing for surface area, right? Those satellites and probes had limited surface area for the solar panels. So they really wanted to prioritize PV materials and device types that optimized for efficiency, because efficiency means higher output per unit of surface area of your panels. Another early market for solar PV was off-grid applications, because as we'll talk about, the costs of solar PV have come down significantly over the past decade plus. And so early applications could only compete in kind of high value applications where the alternatives like connecting to the grid were too expensive. But really, in the last 2 decades, the costs have come down and we've seen on-grid applications take off. Okay, so let's talk about the different material types. PV uses energy from sunlight to move electrons around in semiconductor materials in a controlled manner to generate a current. Certain materials like semiconductors exhibit a property known as the photoelectric effect that causes them to emit electrons when they're hit by sunlight or photons. So a PV panel puts 2 layers of semiconductor materials together that each have different impurities introduced into them through a process called doping, where one layer of the material is doped to have a spare electron, and it's known as the N-type or negative layer. And then the other layer is doped to have a missing electron, so known as the P-type or positive layer. And so the boundary or interface between those 2 semiconductor materials is what's known as the p-n junction. When photons hit the PV panel, electrons are knocked loose from the atoms in the semiconductor material. And if electrical conductors connect these 2 materials together on the positive and negative sides, that forms an electrical circuit. And the flow of electrons through that circuit can generate electricity. So this process is known as, it generates direct current or DC electricity, which is, of course, very different than the traditional way that we've generated electricity through the thermoelectric generators that we've primarily used to generate electricity that produce AC power. The solar cell is the basic building block of a solar PV system. So an individual PV cell, it's not that big. It's about 4 inches across. It can typically produce about 1 to 2 watts of power. So to obtain a useful voltage and more easily harness the power output of PV cells are wired together in series to form larger units called modules. Modules are also called panels, and modules typically have hundreds of cells wired together and can be anywhere between about 300 watts in capacity to 600 watts in capacity. And modules can be connected together to form larger arrays in a project. One concept that's important to understand about solar is that the power output of a module or modules connected in series is limited by the current produced by the least efficient cell. And the current produced is determined by how much light hits that cell. So because of this, if a portion of your module is shaded or dirty, it reduces the power output of your entire module that's wired in series. So it's similar to the analogy of water flowing through a pipe. If you have a blockage in your pipe in one part of it, it restricts the water flow in the rest of your pipe. And so because of this, consideration of shading when you're siting your solar project is really important. I can't tell you guys enough how many stories I've heard from the field of a solar project that's been sited on somebody's rooftop or carport that gets shaded. A portion of it gets shaded at some point during the year because the solar installer or solar contractor didn't do some sort of shading analysis when they were installing the project. And they don't necessarily have an incentive to do that, right? Because they're just installing the project. They're not the ones actually benefiting from the production. So this is one of the things that we actually do when at the Nevada Clean Energy Fund, if we're funding or supporting a solar project, we make sure that that contractor has done a shading assessment at the site so that they're not putting solar panels on in an area that gets shaded. And it's also relevant, when you're thinking about utility scale projects, your panels, if you don't space them away from each other enough, they could shade each other at one point during the day. Or if your land isn't flat, that could create additional shading dynamics between your panels. So there are a variety of different semiconductor materials that are used in solar PV. And the most common material used in over 95% of applications today is silicon, of which you really have two different types. You've got monocrystalline silicon and polycrystalline silicon. That's mono-Si and psi. So mono-Si is grown in a large single crystal called an ingot. And polycrystalline silicon, it has multiple crystals, obviously, as you can assume by the name, and it's made by casting silicon in blocks or grown as a thin ribbon. And mono-Si will have higher efficiencies than polycrystalline silicon because it's more pure crystal. But polycrystalline silicon is typically easier to manufacture and have lower costs. You've also got a broad category of semiconductors known as thin film semiconductors that are characterized based on how the material is manufactured and the resulting thickness of the material. Thin film semiconductors, though, can use a variety of different materials, including amorphous silicon or SIGs, but the most common is cadmium telluride or CadTel, which is primarily manufactured by a company called First Solar. And you can see that CadTel makes up, thin film is only, at least in 2023, made up only 2.5% of global production. And that was, the vast majority of it came from cadmium telluride. So thin film semiconductors are typically manufactured by depositing the material on a substrate like glass. And the result is that it's a very thin and flexible and also typically easier to manufacture material. There are a variety of factors that might lead you to choose one type of material over another, including cost, but also things like temperature sensitivity, how that power output degrades over time. But a really big factor is efficiency, and the efficiency of converting solar energy into electricity. So let's dig into this concept of efficiency of solar panels. So as we talked about earlier, higher efficiency means greater power output per square foot of PV cell. This NREL chart, a National Renewable Energy Laboratory chart, it shows the best efficiencies achieved in a lab for different semiconductor materials and device types over time. Something to keep in mind when looking at these efficiencies is that lab efficiencies are going to be higher than the efficiencies that you actually see in the field. So mono-Si and polysilicon cells are the most prevalent worldwide, as we talked about, and those are the ones in blue up here. These two materials, they don't necessarily have the highest efficiencies of all the different materials, but they really strike that right balance between efficiency and cost, which is why they're the most prevalent. And then you've got cadmium telluride in green with the yellow, the main one with the yellow fill up there, that has about 23% max efficiency that we've seen in the lab. It's only slightly less efficient than silicon cells, but has achieved faster efficiency gains in just the last decade. So the max theoretical efficiency for a single junction solar cell is 33.7%. But we can see in this chart here that a lot of the solar cells have achieved efficiencies higher than that. And those are the ones in purple. These are the multi-junction cells that are made up of multiple types of semiconductor materials stacked on top of each other, each with their own PN junction. So that's why they're called multi-junction. A little bit of context on multi-junction cells. Different semiconductor materials have different what are called band gaps, which is the minimum amount of energy required to knock the spare electron loose of its bound state. And different wavelengths of sunlight have photons with different amounts of energy. So multi-junction cells, what they do with the multiple semiconductor materials is they're able to absorb a wider range of wavelengths from the light spectrum. All right, and that's how they achieve these higher efficiencies. But they're generally more expensive, so we only really see them in high-value, hyperspace constrained applications, like in the space industry that we talked about earlier. Another method for increasing the efficiency of a solar cell is by using reflectors or concentrators. So similar to concentrating solar power, you've got concentrating solar PV, where reflectors concentrate sunlight onto PV panels. And that's known as I said, as concentrating photovoltaics or concentrating PV. We've seen some concentrating PV built, but not a lot, because generally the additional investment in all those moving parts hasn't proven to be worth the additional productivity or efficiency increases of the panels. So because of that, we're seeing very little growth in concentrating PV today. And then another semiconductor material or PV panel type that I want to call out is the perovskites. Pure perovskite cells up here are the orange-red circle with the yellow fill. And perovskites are an emerging PV technology that, even though it's still in R&D phase, research and development phase, hasn't really been commercialized yet. It's generated a lot of excitement because of the rapid lab efficiency gains that have been achieved in such a short period of time. So you can see that the lab efficiencies of those perovskite cells have increased from less than 14% to over 25% in less than a decade. And that's a feat that took silicon cells about 60 years. So really significant efficiency gains. But perovskites continue to face significant challenge in terms of commercialization because they tend to degrade quickly when exposed to sunlight or to heat, which is a problem if you want to use them to generate electricity from the sun. But definitely something to keep an eye on as research on these continues. Another big and recent innovation that's happened in solar PV is what's called bifacial solar panels using PERC technology. And effectively what that does is puts PV technology on the back of solar panels to capture additional reflected and refracted light. The result is that bifacial PERC technologies can increase a PV panel's productivity by 10 to 15%. And installed capacity of bifacial cells has grown from pretty much nothing in 2015 and 2016 to making up the vast majority of manufacturing capacity in PV panels worldwide today. So it's a great example of how innovation continues to happen in the solar industry and driving greater growth. One of the other interesting things for bifacial solar panels is obviously you would want as much of a reflective base underneath your solar panels as possible to reflect that light back. It's a consideration when you're installing a solar project. You might want like white granite rocks underneath your solar panels to help reflect that light back. So let's talk about what affects the capacity of a PV panel. So the maximum power output of a PV panel is typically measured under what are called standard test conditions, which is 25 degrees Celsius at an irradiance of 1,000 watts per meter squared, which is basically the irradiance of when, at the equator, when the sun is at a 90-degree angle to the Earth. And also with an air mass of 1.5, which means very little particles in the atmosphere to disrupt the sunlight. But in reality, in the field, solar projects don't typically operate under those conditions, right? For example, 25 degrees Celsius is 77 degrees Fahrenheit. but often solar PV projects are located out in the desert where sunlight is greatest, but it's also where you have much hotter temperatures. And silicon in particular experiences what is called degradation at higher temperatures. All PV material types experience some form of degradation when exposed to higher temperatures, and you can see the impact here in the lower right-hand chart, but silicon in particular is sensitive there. Sorry, degradation, but also reduced power output. So the other thing to consider is that solar PV capacity is often given in DC or direct current, but what our grid runs on is AC, right? So DC doesn't account for inverter losses, which can be anywhere between like a couple percent to 5% to 8%, depending on your inverter. But if you do see capacity rated in AC for solar panels, it accounts for inverter losses, and it also typically reflects not standard test conditions, but what are called performance test conditions, which are much more reflective of the conditions in which a solar panel is going to be operating under. So the AC rating for a solar PV panel is typically 20 to 25% lower than the DC rating, accounting for all these different factors. And it's something to keep an eye out for because a lot of the industry data out there for solar is in DC, and I've seen journalists and whatnot make mistakes of trying to compare those to AC data from, say, the EIA and make incorrect assumptions and conclusions. Solar PV panels, they also experience degradation over time, and some more than others. The causes are not all that well understood, but it's something to account for when modeling and designing a solar PV project and its economics and productivity over time. Okay, so we talked about the PV materials and panels. In addition to the panels, there's also what are called the balance of system components, the non-module components, which include like the racking system, the structure that holds the modules. They include the inverter to convert DC to AC, all the fuses and cutoff switches, etc. In terms of structures, modules can be held by a structure that's a fixed tilt system, and it doesn't move, or you can have a structure that includes a tracking system that allows your panels to track the sun as the sun moves through in the sky throughout the day. So there are two types of tracking systems. You've got single-axis trackers that rotate your panels in two directions, and those can typically achieve a 25 to 35% increase in productivity over a fixed tilt system. And you've got dual-axis trackers that can rotate in multiple directions and achieve another 5 to 10% boost over single-axis trackers. In practice, we don't see a lot of dual-axis trackers because the added investment and the additional operations and maintenance costs of maintaining those moving parts doesn't really offset the additional productivity, the incremental productivity gain from using those. But generally, in utility scale applications, the vast majority of them that we see deployed use single-axis tracking. Rooftop systems, they don't generally have tracking systems installed. They're typically fixed tilt for a variety of different reasons, including the fact that a building might be surrounded by other buildings or by trees, so tracking may not end up getting the additional productivity boost that you'd like because of that limited solar exposure around buildings. But also, roofs are often weight constrained, right? And can't necessarily take the additional steel that would require to install a tracking system. So that's the PV technology. Let's talk about the role that solar is playing in our energy mix and what kind of growth we're seeing in the market. So significant growth, as we've been talking about. And initially, maybe 15 years ago, that growth was really driven by policy support in different countries. like in Germany, driven by their aggressive solar feed-in tariff, which is kind of like net energy metering. But as solar PV costs have come down, many countries have actually phased down or out a lot of their domestic subsidies for solar. And so today, really the overwhelming driver of this growth that we're seeing is the economic competitiveness of solar PV. Germany was really an early leader in solar PV installations, but they were quickly surpassed in 2015 by China as the installed capacity leader, and China remains the leader today. But we're also seeing a lot of growth in other countries around the world like India and Mexico, and emerging markets in smaller countries in Asia and Latin America as well. So let's look at where we make PV panels and PV panel manufacturing. So in 2005, PV manufacturing was largely concentrated, again, in Germany, and with some capacity as well in the US and Japan. But since then, we've seen manufacturing hubs largely shift to China. And that's because starting around 2008, the Chinese government subsidized significantly their domestic solar manufacturing industry, in silicon PV cells in particular. So today you can see in the pie chart on the right here, the over half of PV modules are built in China, either by Chinese companies or by companies like Canadian Solar or what's another example? Canadian Solar is a Canadian company, but most of their manufacturing capacity is in China. So common theme across our many energy resources in this class is that geopolitical challenges can surface because of, and solar is no exception to that, where a trade deficit with China on manufactured solar PV cells and modules has caused a lot of policy action and a little bit of whiplash in the solar industry as a result. So in February 2018, Trump put in place some tariffs on solar cells imported from China, and that's something that Biden extended in February 2022. And as we've talked about, before in this class, the Biden administration too has made a huge investment in domestic manufacturing of clean energy technologies, including solar panels, through production tax credits for manufacturing for solar manufacturing facilities, but also domestic content requirements and Build America, Buy America requirements applied to federally funded solar projects. Because of the big domestic investments that the US is now making in manufacturing and a manufacturing resurgence that we're seeing here in the US, we are seeing more solar PV manufacturing capacity slowly come online. But I can tell you, it is impossible to get Buy America compliant PV panels today. Hopefully it won't be that way a year from now, but it's creating significant challenges in implementing our 156 million Solar for All award, as it is for many other awardees of federal funds. Okay, so this is zooming into the US. This shows the growth trends of solar PV in the US, looking back historically, and also what's forecast to happen under current policy conditions. And it breaks out that PV by different categories. You've got residential, non-residential, and utility. And a lot of the kind of up and downs that you see in that growth, you see is attributed to a variety of different factors. You've got a little bit of whiplash with tax credits, like in 2016. The industry thought that the investment tax credit was going to sunset, but it was ultimately, so they made a huge investment in solar that would start construction by the end of 2016. But ultimately, those tax credits were extended. More recently, in 2024, you see that slight decline compared to 2023, and that's largely because of macroeconomic factors like supply chain constraints and higher interest rates that are creating some challenges in the capital stack of the projects that are in the works. But we're not necessarily seeing projects not happen, we're just seeing them get delayed. So pushed into 2025. All right, let's talk about some of the policy drivers that support this growth in solar energy. And there are a lot of different ones, right? You've got the renewable portfolio standards and 100% clean electricity targets that many states across the US have in place. There are RPS standards in over 2/3 of the US. You've got the Public Utilities Regulatory Policies Act, which was an early driver of not just natural gas, but also renewable energy projects coming out of the 1980s and the oil crises then. You've got the investment tax credit and now the production tax credit, those federal tax credits, the PTC and the ITC that we talked about in the Introduction to Renewable Energy lecture, that could cover anywhere from 6% up to 70% of the capital cost of a solar project. So those are pretty significant for solar energy, as well as for other renewable energy resources. And then you've got the, this is all at the federal level, the $7 billion Solar for All program administered by the Environmental Protection Agency. This is a program that's part of the Greenhouse Gas Reduction Fund that was created out of the Inflation Reduction Act to provide funding for solar projects that benefit specifically low-income households. And then, another significant policy that really enables residential solar to happen is what's called net energy metering, where the utility buys back excess generation from a rooftop solar project. All right, so lots of different incentives out there relevant for solar energy, both at the state and local level, as well as at the federal level. As we've talked about in this class before, another important trend and characteristic of increasing solar on the grid is the challenges of integrating that intermittent resource, where we have increasingly a huge amount of solar on the grid during the day, but significant ramping needs in the morning when the sun is rising, and particularly in the evening when the sun is setting, simultaneous to when we have a peak in demand on the grid. So that huge ramping need, 16 gigawatts over the course of 3 hours, is a challenge that grid operators and utilities need to meet because of the increasing solar resource. So this is what's known as the duck curve, with the neck of the duck being representing that ramping need. And I know you guys had the Energy at Stanford lecture and learned about the fact that the university is sourcing 100% of its electricity needs, largely from 2 utility-scale solar PV projects in the Central California through 2 power purchase agreements. But they also have a good amount of solar on campus, on rooftops and whatnot as well. I want to call out a small but interesting application for solar PV, what are called building integrated PV, which is replacing conventional building materials used in walls, windows, or roofs with PV materials themselves. This building integrated PV generated a good amount of hype several years ago when Tesla came out with their solar roof tiles, but the product has really since struggled to achieve any meaningful scale and positive economics. So building integrated PV, it's got a huge potential market, right? Any building material that's exposed to the sun, but it's a really hard nut to crack for a variety of different reasons. Cost is certainly one, as we saw with the Tesla solar roof that was about $10,000 more than a typical solar PV project on a roof. Also, just the building construction and design industry is a very conservative industry and market to crack to break into. It's really hard to find architects or building contractors that are willing to go out on a limb and try a new technology that they don't have experience with. And also, there's really only a limited portion of the building stock that turns over, right? Building integrated PV, I think about 2% of our building stock is new construction in any given year. Of course, you got retrofits, things like roof replacements as well, that where building integrated PV can be leveraged, but it's still small relative to the overall market. So because of these and other challenges, building integrated PV market will probably continue to remain niche, but there are still a lot of really interesting companies that are operating in that space, including some with Stanford origins. Another application I want to call out for solar is off-grid applications that are particularly relevant in the developing world for communities that wouldn't otherwise be able to cost-effectively connect to the grid. Early applications for solar and off-grid were really focused on things like small applications like a solar lantern or a solar cell phone charger. But as the costs of solar PV have come down and as the costs of batteries have come down as well, we've seen solar deployed in much bigger applications for communities with community scale solar PV and storage that can deliver 24/7 electricity access for a wider range of energy needs. And there are companies like D-Light and Zola Electric that are focused in that area. Let's talk about the environmental impacts of solar PV. And I'm going to go through this somewhat quickly, but generally, solar PV has much lower environmental impacts than their fossil fuel counterparts. No air pollution, no greenhouse gas emissions, minimal water use, except if you want to wash your panels. If dust accumulates on your PV panels, it can really decrease the productivity of your panels. But PV panels, they do have some environmental impacts that need to be managed, including land use, end-of-use recycling, and we talked about in land use, like the impact of the desert tortoises of PV panels, and concentrating solar projects as well. But I want to dig into two myths that I commonly hear about solar PV and its environmental impacts. One myth is that it takes more energy to manufacture panels than the energy produced by the panels themselves over their lifetime. And that's simply not true. This chart here shows a study of the energy return on energy invested of different types of solar PV technologies, solar panel, technologies. And EROI, energy return on energy invested, takes total energy produced from a solar project over its lifetime over the total energy required to manufacture those panels. So the higher the EROI, the better. In this chart, it summarizes about 230 different research papers on the topic and found that most solar panel technologies have an EROI of 10 to 30 times plus. Another way to look at this is based on energy payback period, and typically solar panels will pay themselves back within the first year of operation. And I want to call out this study. It's a great study because it's very comprehensive, but it is from about 10 or 15 years ago. And as efficiencies have increased for solar panels, we've gotten more efficient at manufacturing them. That EROI has increased even more. Another myth that I commonly hear is that solar projects take up a lot of land. But as we talked about in the environment lecture, it's important to look at the entire life cycle, right? Because solar projects don't have any upstream resource extraction land requirements. So if you look at for the fuel production itself, right? Because it's just the fuel is the sun. So if you look at solar PV, power plant area compared to, say, a coal or nuclear or natural gas facility, including fuel time production, it's actually quite comparable. But still, solar does use a lot of land, and that can create some challenges for the power project itself. And that can and has created challenges in communities that don't want to see, say, agricultural land converted for solar PV usage. But there are some really interesting applications for solar that don't necessarily use land in that way, like floating photovoltaics that are sited on reservoirs or canals that also help to reduce water evaporation. Or agrivoltaics, where we've seen solar projects that are still being used for crop growing underneath the panels that require less light. And then, of course, you've got rooftop solar that doesn't use any land. Okay, so let's end by talking about economics. So we've seen really steep reductions in the cost of solar PV, and much of the cost declines in about the 2008 to 2012 timeframe have been because of innovations in manufacturing scale in the module themselves. But since then, we've seen slower declines in the module costs as kind of the low-hanging fruit innovations have been taken up. Really, most of the reductions and focus on cost declines that we've seen since then have been from the balance of system costs, right? The non-module soft costs. And you can see that those balance of system costs in the breakdown of PV project costs on the right here make up the bulk of the costs of these projects. Module costs now make up less than 50% of the total system cost, particularly when you're looking at like residential rooftop solar where customer acquisition costs are really high, but you also have things like the cost of the inverter, the mounting structure for the module, et cetera. All right, so let's revisit these LCOE numbers and really dig into them. So you can see LCOE varies significantly depending on the scale at which you're deploying solar PV. And one of the first things you probably notice is that residential solar PV is about 5 to 6 times more expensive than utility scale. Well, another key factor in this difference is, like we talked about earlier, you can't put a tracking system on a rooftop. So the productivity of a rooftop solar system is typically going to be significantly lower than the productivity of a utility scale system that has that dual axis tracking that can result in a 20 to 30% production boost. In many markets across the US, we have net energy metering, right? Where these projects, rooftop projects, get compensated at or close to the retail rate of electricity. But if you'll remember from the grid lecture, the retail rate of electricity doesn't just include the costs of generating electricity. It includes all the costs for the transmission and distribution system. And you might be thinking, well, if I have a rooftop solar system, I'm not using the transmission and distribution system, am I? Actually, unless you have a really big energy storage project located with your solar PV project, you are using the grid. You're using the grid effectively as energy storage, right? Where typically in a home, people use the most energy in the evening after the sun has gone down. That's the whole dynamic with the California ISO duck curve, right? So even though rooftop solar, households with rooftop solar are still using the transmission and distribution system, they're not paying the costs for the use of that transmission and distribution system because they're getting the retail rate for their electricity rather than the wholesale rate. If rooftop solar projects were only compensated at the wholesale rate, they would not be economic. They wouldn't be able to cover their costs because of the higher LCOE. So because of this dynamic, customers that have rooftop solar, if they're being compensated at the retail rate through net metering, are actually shifting the costs of the transmission and distribution system onto customers that don't have solar. And because of this, it's one of the reasons why the Edison Electric Institute several years ago coined the term the utility death spiral, because as more and more customers get rooftop solar, that means that they're unable to recover their costs for the grid. and they have to raise rates for everyone else, and that results in higher incentives for everyone else to go solar, ultimately bankrupting the utility. But what we've seen over the past several years is utilities kind of fight back and adjust rates so that rooftop solar customers are paying for use of the transmission and distribution system through things like fixed costs or changes to net metering rates, or even just changes to retail rates like time of use pricing. The other way that the federal government is trying to address these inequities, because oftentimes rooftop solar is deployed for higher income customers that have control of their home, control of their roof. They have the capital to invest in a rooftop solar project and reap the benefits involved. So that's why those inequities in access to rooftop solar and the cost benefits are a reason why the Inflation Reduction Act included that $7 billion Solar for All bucket of funds administered by the EPA, really to provide that access to capital for low-income customers, whether you're talking about customers in affordable multifamily housing or in single-family households or beneficiaries of community solar projects. So EPA made several awards, almost one award per state, and we're administering the Solar for All award in Nevada, $156 million, that we're going to be deploying over the next 5 years for low-income solar projects. All right, so that's the solar resource. Thanks, everyone.